found propositions, whether those are valid or not. And we figured that if you construct a truth table and the truth table gives us a tautology, then those propositions are valid, and if there is a contradiction, those are invalid. And if there is in-between statements, then their validity depends on particular values of those atomic propositions. Right. There are certain situations which we have not covered yet, okay, which creates some sort of problem. And that's what we're going to do today. So propositional logic has limitations. What sort of limitations we have? However, sometimes this is inadequate because it can't cope with logical structure that may be present. For example, consider the argument. It is not true that all animals are cows. Therefore, there is at least one animal that is not a cow. Looks like it's a true statement, but how are we going to model this? There is some kind of argument, at least one. It put us in a situation where we have to quantify that. What we mean by at least one? Could it be 3, 5, 7, 8, or something like that? What are those numeric numbers? So we have to introduce now new parameters in propositional logic. Previously we studied 5 connectives, right, which were and, or, not, if and only if, which is equivalent to or implies, implication. 5 connectives that we did for propositions. Now we're going to study slightly more. Connectives are still the same, but now we're going to study another thing here, which we call that as predicate. So, so this seems perfectly reasonable argument. However, so let's try to analyze the argument. We'll test the validity of, it is not true that all animals are cows, therefore there is at least one animal that is not a cow. Start by defining atomic propositions. Let P be all animals are cows, and Q, there is at least one animal that is not a cow. Okay? We're just starting by this. Then the argument has expressions not P. Okay? Not P means not all animals are cows. That means there is at least one animal that is not a cow. Is this expression a tautology? You can quickly make it. Let's say P is true, true, false, false, and Q is true, false, true, false. Not P would be false, false, true, true, and not P implies Q would be. Now you're looking at not P implies Q. So tail is false. Tail is false, whatever head is, this would be a true statement. Now, tail is true, and the head is true, that's a true statement. Now, tail is true, but head is false, that's a false statement. So you can clearly see there, it's not a tautology by drawing this table. Okay? So, but the statement looked, from the wording, if you look at that, it seems like this is a perfectly reasonable argument. If you say that it's not true that all animals are cows, so we're given a fact, premise, not all animals are cows, so there is at least one animal that is not a cow, in other words. Okay? So that looked like a true statement, a valid statement, but when we tested through propositional logic, it gave us a different answer. So it doesn't seem logically valid from here. So there is something missing here. And that missing part is that we have to quantify it. So what's the problem? We are unable to break down further the atomic propositions. So all animals are cows, we cannot further break it down, and we cannot further break this sentence down as well. So to achieve this, we introduce the predicate logic. Predicates are very, very important. By using them, we are able to quantify many statements. So what is predicate? The definition of predicate is, a predicate is a statement containing one or more variables. If values are assigned to all variables, the result is a proposition. It's like, x plus y. Okay? It doesn't make sense until you say x is 2, y is 3, then this is equals to 5. Okay? X and y at their own does not make sense until you assign them particular values. Right? That same goes here. Predicate is a statement which would have some variables, and those would only make sense if you assign certain values to them. Let's look at examples. Y greater than equals to 7 is a predicate. That means y is a variable, that is a real number, and we are saying the values of y are greater than equals to 7. Okay. Do you agree with that? This is sort of an example of a predicate. Okay. X is in Africa is a predicate where X is a variable denoting the name of a country. So this is also a predicate. So X is in Africa is a predicate, and it is a proposition if you assign certain value to it. For example, South Africa is in Africa. Mozambique is in Africa. Chad is in Africa. New Zealand is in... Yes, I agree with you. New Zealand is also in Africa.
Victoria, East London, Africa.
Is it?
No, it's not.
No? All right. So the statement is wrong when I say New Zealand is in Africa. Right? So it's a proposition. So even if it's false. So propositions from predicates. A proposition can be obtained from predicate by means other than allocating values to variables. Okay, look, from the predicate y greater than equals to 7, we can obtain the proposition for all y which are greater than equals to 7. Okay, that's also an example of a predicate. So, and this statement is false. Can you tell me why? Exactly. There is a number 6 which is not greater than 7. When you say for all y, when you say for all y, that means these are all real numbers. Okay? Greater than 7 is another part. Since all real numbers are not greater than 7, this statement is clearly false. How I can correct this statement? What sort of modifications I do here that this statement becomes a true statement? So instead of for all y, if I say there exists y such that these are greater than equals to 7, this is a true statement. Because there are some y's which are greater than 7. There are some real numbers which are greater than 7. So it is true. Okay. So just like it is true that y is greater than equal to 7 for some values of y, or there exists y such that this is true. Okay. So for all and there exist are called quantifiers. Where you quantify them, you're giving them some particular weights, values in other words. The process of applying a quantifier to a variable is called quantifying the variable. And if it is quantified, it's said to have bounds, something like that, so you don't have to know this. Okay, there exists y such that y is greater than or equals to 7. The variable y is bound by the quantifier there exists. So this is just some technical thing. Okay. Otherwise it is free. Now let's look at some notations for predicate and quantifiers. So use capital letters to denote predicates. Okay. Now we are on actual examples that we are doing. A predicate P that contains a variable x is denoted by Px. Right. If P contains both x and y, it is denoted by Pxy. For all is denoted by for all, like upside down A. There exists is denoted by reversed capital E. Now, write in symbols. Now, we have denoted few things. Px is a predicate when the variable is 1. If there is a quantifier for all, we'll write it like this. And if there is a quantifier there exists, we write it like that. Now, given that you have this, can we write this statement in symbolic form? There exists y such that y is greater than or equals to 7. Now, here, I can write it like reverse E. Okay, there exists y. Okay, and then you can say y greater than or equals to 7. This is one way of writing. And the other way of writing is there exists y such that py. What is py? Where py is equals to y greater than or equals to 7. It's just that predicate. There is only one variable here, y, and we write it in this form. So remember what we are giving here, we have given some notations, and after that we just replace those notations. For example, quantifier, this reverse E stands for there exists. This upside down A is for the quantifier for all. Okay? And if you write P of X is a predicate of variable X, containing variable X. Yeah. Predicate and there is a variable X. Three just new symbols that we did here. Okay? Now, based on this, let's write this statement down in symbolic form and see what we have. So there are two ways, as I said. Let Py denote the predicate y greater than 7. I briefly wrote it down in the just a moment ago. Then the proposition can be written as there exists y and the predicate py, where py is stands for y greater than or equals to 7. Alternatively, you simply write this as here's the example. There exists, replace that with this reverse E. There exists y, and y is greater than or equals to 7. This is just the symbolic form. You know what we are going to use? We're going to use these notations later today in this lecture to say that, okay, how are you going to book taxis or cars and all that using this system? Exactly the same way. And you can put some restrictions. For example, if you're only allowed to book one car on a certain day, then how do you book it? How do you feed into this system? Yeah. Okay. Another example. Write in symbols for all y is less than 7 or y is greater than or equals to 7. Now, can you write this down using symbols, please? And then I will write it down in a few possible ways. Remember, for all is upside down I. And then there are two expressions, y less than 7 or y greater than equals to 7. So you may want to start by writing the predicate. Let py denote y greater than equals to 7, let's say. Yeah? You agree with me, right? Okay. So then what this is going to be? For all y, one way you can write it down as for all y less than 7 or y greater than equals to 7. This is one way of writing. Second, for all y, now we said py to denote y greater than equals to 7. So we have py. What would I have here then? If I'm writing in this form, then y greater than equals to 7 is py. What would be y less than 7? Absolutely right. Yeah, not py. Done. This is exactly the notations that we're going to use. So far, for quantification purposes, we only need 2 new symbols. They exist and for all. Nothing else. All other symbols we already know. Questions? Look simple? No? Come on. It should be simple, I think. So, look, here we defined 2 different predicates. I have not used them when I was doing the example because I totally forgot that you can define 2 predicates. However, 2 predicates are related the way you explained to me. All right? So, but in any case, you can define 2 predicates, py to be y less than 7 and qy to be y greater than equals to 7. Then you have for all y less than 7 or y greater than equals to 7. That's one way of writing. Second, so you can say exactly the same way as we started. For all y, either you have py or you have not py. Means y less than 7 or y not less than 7. Okay? So this is another way of writing, whatever you guys are comfortable with. Now, there are lots of examples I'm going to do. As I said previously, essentially when I said there are 3 variables, we're done there. It's just for understanding purposes, I'm giving more and more examples. Okay? Now, what happens if you have 2 variables? Write the following 2 propositions in symbols. For every number y, there is a number x such that x is equals to y minus 3. Now, think hard on this statement and tell me whether what you think of this statement. Is it a true statement? I don't want to confuse anybody. It's just that I want to know what you think of that question. Is it valid, true, false, what it says? True. You think it's true?
False.
Who says false? Clarify that, please. Now, of course, you have to clarify. It's not that, okay, it's true or false.
I don't know, just something in my head says false.
Anyone else?
Little ink X can only be one.
That's precisely right. Look, we're saying for every number y, there is a number x. So suppose you put x is equals to 2. Yeah? The statement is clearly false because we're saying for every number y, if you put x is equals to 2, there is only one number y. For this, that statement can hold. Otherwise, it is false. Look, it says for every number y, there is a number x. Okay? Suppose x is 2. That means y has to be 5. It's not true for all y. Yeah? So the statement is clearly false. Agree? Now, there is a number x yeah? So what I said? Yeah, probably I was wrong. No, I was right. Absolutely right. There is a number x such that for every number y, so you can do that. So let's look at this. How are we going to put that? So there are two variables involved, x and y. So you can write pxy denotes the predicate x is equals to y minus 3. So you can write the propositions as, so for all y, the first one, when you say for every number y, for all y, there exists x such that this statement holds. Yeah. And the second one would be, what would be the second one? You switch them, and you would have, for the second one, there exists x such that for every y, that statement holds. Yeah. Okay. Now we come to the question again. I have to test myself as well. Slightly I put the confusing statement up there. Okay. Are the above proposition true or false? For one, we said for every number y, there is a number x such that that holds. Yeah. So the commas are matching. Okay. So you have x is equals to y minus 3. You have x, you have y, and your equation is when y is 0, x is negative 3. You know that, right? And when x is 0, y is positive 3. So you have this line, right? X is equals to y minus 3. Now it says for every number y, there is a number x that this equation holds. Yeah, look like the first one is true, second one is false. Yeah. I was lost in the words actually there. So for every number y, the graph made it clear. For every number y, when I pick, there exists a number x such that this holds. However, here we are saying there is a number x. Now fixing the number x first. So where I mucked it up previously was I fixed number x first in the first situation, which I should not have done. All right, that's where I explained it incorrectly. So there, I should not fix the number x first because my statement is coming from for every y to start with. Right. Okay. So clearly this one is false because if I fix number x, the statement is not true for all y. Okay. And the first one, I'm letting y free. If y can be chosen any, correspondingly you will get x. So obviously one is true and two is false. Any questions? Confusions happen, you know. You know.
If we get confused during the test today, can we just write confusions happen?
No. No. You're not giving me marks. You're not giving me marks. I'm giving you. You know, I'm testing you.
Keep on telling us all these slides.
Oh, it's natural.
So
It's natural. When you're teaching logic, I tell you what, when you're teaching logic, anyone can stop you. Trust me on that. Anyway, let's move on. Now, what are the practical applications of predicate notation? Let's look at some examples. In the specification of a system, for example, a database, for recording bookings for a car hire business, suppose BCD denotes the predicate car C is booked on day D. Right? So what is the predicate? B, C, D means car C is booked on a day D. Put each of the following sentences in symbolic form. The Corolla is booked on September 7th. How you would write it down? What you think? Have you written it? Okay, so how I would write, the Corolla is booked on September C, so basically this is simply B of Corolla September 7. Simple as that, because there is no other statements at all. So it says there is a car and it's booked on September 7. Okay, what's the car? Corolla, and booked on September 7. Right. We move on to slightly more. There are 7-8 examples we're going to do, and every example has certain features different to the others. Right. So if we can understand all examples, predicate logic would be clear to you. Now, question, the Fiesta is not booked on August 5. What do you think of this? The Fiesta is not booked on August 5. Remember, when you look at that predicate B, C, D, there is no quantifier or connective inside the brackets. So we are not going to put any quantifier or connective inside the bracket. So suppose you want to say Fiesta is booked. Now there I quote Borat joke that says, you would have watched the movie by now, I guess. Okay, so this is B, Fiesta, August 5, not. So suppose it is booked, right? You're going to say B, Fiesta. If I ignore this not sign, it would be that Fiesta is booked on August 5. And then you put not outside to say that it is not.
All right, well, you just
You're reading me.
Fiesta as well.
What's that?
Isn't that not Fiesta as well? Simply not Fiesta.
Yes, that is also true. When you put Fiesta, you're fixing the car there, right? And if you ignore not, that means Fiesta is booked on August 5.
What about return on August 7?
What?
What about if you return also on August 7?
7?
Yeah.
I don't get you. What you're saying?
Like if you book it and you pick it up on August 5 and you return it.
This
on August
computer.
7, what would that symbol be?
All right. Anyway, now move on. So if I put not inside, the quantifier doesn't go inside. As I said clearly previously, we don't put any quantifier inside. Yeah. So it is incorrect. So as again say, this corresponds to single car, single day. This predicate B, C, D corresponds to single car, single day, right? So, and there can't be extra details, so you can't put any extra connectives or anything, right? It will not read it. Let's look at examples. If BCD denotes car C is booked on day D, put the following in symbolic form. Cars C1 and C2 are booked on October 4. How are you going to do that? Now there are two cars booked on one day. So car C1. So you will write it B bracket C1 comma October 4 and B C2 comma October 4. Now what other detail I have to give about C1 and C2? What other ways I can write? I can say that there exist cars C1, C2, and then I write BC1 October 4 and BC2 October 4, and then I have to say C1 is not the same as C2. They are different cars. If I put C1 equals to C2, of course, then there is only one car. Here we are saying two different cars, right? That's the way of writing as well. Yeah. So one way here is you only write this because you are given C1 and C2. Yeah. So you're given C1 and C2, so you write it down. But suppose you are not given C1 and C2. Suppose you are given, there are two cars. Two cars are booked on the same day. Two different cars are booked on the same day. Then you have to declare those cars. You would have to say that Fiesta and Corolla, for instance, are booked on October 4. Or you would say that there exists C1, comma C2, such that BC1 October 4 and BC2 October 4. Okay? And you would not write this down. As I said previously, quantifiers don't go inside brackets at all. It's wrong if you do that. Okay, let's move on. Now, all cars are booked on August 30. How are we going to put that in? So obviously, all cars means for all C, then B, C, comma, August 30. Make sense? So all cars there, you would have for all C, such that B, C, August 30. That means now quantifiers are outside. That says all the cars, all C, all cars are booked on August 30. Okay. Any questions? We're going to complicate this statement slightly. Very similar statement. And car C is not booked on every day. Can you give it a go yourself first? Car C is not booked on every day. So there is a car which is not booked on every day. How are you going to put that? So, what's your answer? Anyone?
There exists a C for all D but not B, C, D.
Say it again.
There exists a C for all D, E, but not B, bracket C, D.
Okay. So it reads as there exists a car which is booked for all days D not. Yeah. So in other words, it's not true that for all days D there is a car booked. Do you agree with that? So this is how car C is not booked on every day. You can interpret that. So you're gonna write it as it's not true that for all days D, as I just said, car C is booked on day D. So in symbols it would be so not you can put not outside or inside is your choice. For all days D, car C is booked, and then you put not outside means for any day D, car C is not booked. Okay. Now this sentence can also be written as, let me write down here. This sentence can also be written down as we said over there. There exists D. Yeah. Okay. So you put that out. Not B, C, D. So you can write it like that as well if you like. Okay. So another method is, as I just wrote on by hand, can also be interpreted as there exists a day D for which it is not true that car C is booked. Right. So there exists a day, and you're claiming car C is booked, not. So this is how we have to explain. Yes. Any questions? Or any other method that you have in mind that you can write this down?
So it's how I write as well, because I did that, but just with the other way around.
Which one?
So there exists C for all.
No, actually, because C is given to us, right? And we are saying C is not booked on any day D. So for all day D, I think we have, this is redundant. This is not needed there because that is given to us. But if you write there is a C, it's true. It's not wrong. I mean, we are repeating the same information that is given to us. So it's okay. All right. Okay. Let's look at. So only variable D is quantified. We don't have to quantify C because, as I just said, it's given in the original syntax. If you quantify that even then, it doesn't, okay, it does not make your answer wrong. All right? Because you are repeating the same information that's given to you. Anyway. All cars are booked on all days. How you do that? Let's look at how you quantify that statement. All cars are booked on every single day. Now you need a car, you can't get one. How are you going to write it down? Anyone?
Is it O, C, D, B, C, D?
For all, C. For all, D. Exactly the same statement I'm quoting, but except you missed one quantifier there. I cannot write, I have to quantify every variable there. For all C, for all D, B, C, D, then it's correct. If I say for all C, D, B, C, D, it only quantifies C. It's not quantifying D then. And there is no quantifier there, so therefore that will make it incorrect. We have to, if we are writing something, we have to quantify that. There has to be a quantifier. I cannot say that C, B, C, D. It has no meanings. What is C? There it is for all. We have to quantify that. Okay? For all C, for all cars, all days, booked.
So we don't need to say and for that, so we don't need to go for all C and for all D, it's just for all C.
For all C, for all D.
Yeah.
Okay. Let's look at next example. All right. Car C is booked on at least 2 days. What do you think of that? At least 2 days. So what that means? So that means there are 2 different days. We have to be sure that the days we are giving or we are quantifying, they are different. So we are saying there exists D1, there exists D2. This is my attempt. You put this slightly different than mine. C, D1, and C is also booked on D2. Remember, car C is a particular car. It's given to us. There is a car C. We don't have to quantify that anymore. Okay? So the car C is there. So it is booked on D. So there exist days. D1, on certain day D1, certain day D2. BC D1 is booked. Okay? And this is also booked on D2. Am I missing something?
Oh, it's at least 2 days.
Exactly. So I have to say that the days are different. So that means I have to say that D1 is not the same as D2. I have introduced another symbol here. This, when you put a line in equality, that means not. So these are not equal. When I say there exists D1, that corresponds to this could be many D1s. So at least we are saying that there is at least one there. Make sense? All right. So we have there exists D1, there exists D2, BCD1 and BCD2, and these two are different days. Okay. Now, think of this question now. No more than one car is booked on day D. So you're fixing a day. You're saying, okay, we are given a day, and we want to say that not more than one car is booked on that day. So you want to make sure that you write in symbols form stating that on a particular day D, there is only one car that is booked, not more than one. How are we going to do that?
All C is less than or equal to 1.
No, we don't use less than equal. I have not introduced that quantifier. So you're only going to use the quantifiers that we use so far. So think of this. There are definitely more than one cars from the look of it. Okay? What we want to do, we want to say that if there are more than one cars and there are more than one car booked on day D, we want to say that if there is more than one car booked on day D, then this statement has to be true for any car C1, for any car C2. If the car C1 and C2 are booked on day D, then this implies C1 is the same as C2. This can only happen when C1 and C2 are the same car. That means we are forcing that even if there are two cars C1 and C2 and booked on day D, we are forcing those two cars to be the same. So this means car has to be the same car. So that means only one car is booked on that day. Make sense? So we are saying cars C1 and C2 are exactly the same. They are the same cars, actually. It's one car only. So this is the way of forcing something to be equal. Any questions? Okay. Then let's look at this. This can be interpreted as if two cars are booked on day D, then they are the same car, as I said, which can be expanded as for all cars C1 and C2. If C1 is booked on day D and C2 is booked on day D, then C1 and C2 are the same car. Basically, so that's what we meant to say. All right. So the statement was no more than one car is booked on day D. Now, I'm going to change this statement slightly. Now I'm going to put that exactly one car C is booked on day D. And then we're going to write it down. So exactly one car is booked on day D. What that mean? Think about it.